Hello, and welcome to a presentation on the Triassic period prepared for the University of Kansas Geology 101 class. The Triassic period represents a 50 million year long period of time in the Earth's history from approximately 252 million years ago to 201 million years ago. This can be hard to visualize, so let's use some timelines to get a better idea of when exactly we are talking about. This timeline encompasses the entire presently accepted timeline of the universe. The universe began approximately 14 billion years ago here. This is the formation of the Earth, which was approximately 4.65 billion years ago. And this is the Triassic period, represented here by the introduction of dinosaurs. Again, this is over 200 million years in the past, and by comparison, modern man, or Homo sapien, has only been around for approximately 200,000 years. If we shrink this time scale to encompass only the history of the Earth, the Triassic period is right here, at the beginning of the Mesozoic era. For more information on time periods in Earth's history, you can visit the International Commission of Stratigraphy at www.stratigraphy.org. Now let's do a quick review. When did the Triassic period begin? A. 2.52 billion years ago, B. 252 million years ago, or C. 252,000 years ago. According to the ICS, the Triassic period refers to a period of time between approximately 252 million years ago and 201 million years ago. Earth during the Triassic period looked a bit different than it does as we know it now. The continents were merged together as a giant supercontinent known as Pangea. It was surrounded by one global ocean known as Penthalacia, with one sea known as the Tethys Sea on the eastern side of Pangea. Towards the end of the Triassic period, rifting began to occur along what is now the North American east coast, represented here by the green arrows. This rift would eventually become the Mid-Atlantic Ridge, creating new oceanic crust and driving the Americas away from Pangea, and creating what we now know as the Atlantic Ocean. And this is why no part of the Atlantic Ocean seafloor is older than 200 million years. Eventually, plate tectonics caused Asia to rotate to the southeast, and India would move to the north, crashing into the Asian continent around 50 million years ago, creating the Himalayan mountain range. If you're finding this hard to visualize, we've included a link below this video to an animation of this process. The breakup of Pangea is recorded today along the United States east coast. The Newark supergroup refers to partially exposed sediment layers between North Carolina and Nova Scotia, which document the early breakup of Pangea. Now, before we go any further, we must touch on the subject of mass extinction events. These events are vital to understanding not only the history of the Earth, but the Triassic period itself. The Triassic period is bookended by two of the five largest known extinction events in the Earth's history. The beginning of the Triassic period is marked by the end Permian extinction, and while estimates as to actual numbers may vary, it is generally accepted that this was the most severe extinction event in the Earth's history. At least 60% of land species and over 90% of ocean life was extinguished by this mass extinction event, and much of the early Triassic was the remaining life that survived, struggling to recover and adapt. The end Triassic extinction event was small in comparison, yet it is still one of the five largest in Earth's history, and came at a pivotal time, as many species we know today are species that managed to survive this event. Now, what was going on that caused these extinction events? Here's an excellent chart that may give us some clues. This chart is a result of work done by Hongfu Yin and Haiyong Song, entitled Mass Extinction and Pangea Integration During the Paleozoic-Mesozoic Transition. On the left here we have age in millions of years, and at the bottom we start at 300 million years ago and we go up to about 200 million years ago, which means the top half of this graph is the Triassic period. And right here in the middle is the beginning of the Triassic period. Now over here on the mantle convection graph, we can see that Pangea is forming. Now Pangea is formed, and here in the middle Triassic it begins rifting and dissolving, breaking apart. Here on the right side is a biodiversity graph. And we can see that there's a lot of life here in the Permian, but as we approach the Permian-Triassic boundary extinction event, the biodiversity approaches zero. This was a massive extinction event at the end of the Permian Age and the beginning of the Triassic. And then we see life start to recover before the end Triassic extinction event. And if we look here under volcanism, we can see this right here, which coincides with the transition to the Triassic period and the end Permian extinction event. There's something called the Siberian Trap. This was a massive flood basalt formation that was active at this time. These were low viscosity lava flows. They're more similar to what you would find in Hawaii as opposed to a single explosive eruption, but their scale was enormous. The Siberian Trap covered an estimated 800,000 square miles. Now that sounds big, but how big is it? The state of Kansas is approximately 80,000 square miles. So that means 800,000 square miles would cover Kansas 10 times over. This is massive. So we have this massive volcanism going on between the Permian and Triassic periods, and we're dumping lots of carbon and sulfur compounds into the environment, creating a greenhouse effect. We can see here in atmosphere and climate that temperatures are cool on the right and warm on the left. And here in the Permian they're cool, and as we approach the beginning of the Triassic they become much warmer, and then eventually stay warm and arid through most of the Triassic before cooling off at the end of the Triassic. But we also see here is methane release. So as the temperatures start to rise due to these greenhouse gases, the ocean heats up and the seafloor heats up, and it starts to release methane out of the seafloor crust. And this just kind of compounds the whole greenhouse effect even more. And in addition, we can see right here that the ocean environment becomes very anoxic, which means there's low oxygen or a lack of oxygen. And this could be a major contributing factor to the fact that 90% of oceanic life died out at this time. And all of these reasons together are reasons why many large volcanic events are being tied to some of these major mass extinction events. For more information on mass extinctions and local geology, you can visit the Kansas Geological Survey webpage at www.kgs.ku.edu. And for more information on the link between volcanism and the end Triassic mass extinction, you can visit the National Science Foundation's website at www.nsf.gov. Type Triassic extinction into the search bar in the upper right, and the top result will take you to an MIT article on the relationship between volcanism and the Central Atlantic Magmatic Province, which was the rifting event that occurred from the break of Pangea we talked about early, and the end of the Triassic extinction. Very cool stuff. Life during the Triassic. The Triassic was a pivotal time for life as we know it. Life was just coming off this massive end Permian extinction, and there were a lot of things that developed at this time that we'd recognize today. Things such as turtles, crocodiles, the reptiles that we think of today, dinosaurs, and mammals are the big ones. Most of these species did not actually appear towards the very end of the Triassic, following what would have been the Carnian pluvial event, which was a period of about 8 million years where the environment, which was warm and very dry, became much wetter and more humid. And this also coincides a bit with the breakup of Pangea. But for the most of the Triassic, most of the land creatures would have been some type of reptile or reptile family animal, and there's a small divergence of synapsids right before the reptile tree, which leads to the mammals and eventually leads to humans. But most of the land creatures would have been known as Archosaurs, and you might think of them as dinosaurs, but they're really not. And this is the Triassic period here, and you can see the tree that starts with amniotes, which is basically egg-laying vertebrate animals whose eggs were adapted to being laid on land. And from here it splits into the synapsids tree, which eventually spawns mammals, and the reptilian tree, which spawns turtles, crocodiles, flying pterosaurs, dinosaurs, snakes, all the reptiles we can think of as today. So what makes dinosaurs similar to other archosaurs? Dinosaurs have similar pelvises to archosaurs. Saurischian dinosaurs have a pelvis similar to reptiles, while ornithischian dinosaurs feature a pelvis similar to a bird. Ankylosaurus congue, one of the oldest archosaurs, shared many characteristics with dinosaurs. Teeth, which were peg-like, signaling an omnivorous or herbivorous diet similar to dinosaurs. Quadrupedal stance on all fours. Beak-like lower jaw, long limbs, and a posterior-ventral directed glenoid, just like dinosaurs. And a glenoid is a shallow depression on a bone. Now, what makes dinosaurs different from other archosaurs? The unique characteristics of dinosaurs can be observed through 1. Bone histology, the study of cross-sections of bone under the microscope. Dinosaurs have highly vascular bones. Before they reached sexual maturity, bone growth was very rapid. This rapid bone growth produced a blood vessel filled with fibrolamellar structure. Bone growth would slow down at sexual maturity, causing its bone structure to be more compact in the dinosaur's outer regions. This growth was so rapid that the dinosaur would reach its adult size in just a few years. Other differences: locomotion, the ability to move from one place to another very quickly. Dinosaurs have a tall stance and a differing limb position, and allowed them to move much faster than archosaurs. Although controversial, some scientists also believe their speed can be attributed to their warm-bloodedness and their differing tall stance and limb positioning. And the other difference was feeding. Unlike archosaurs, it is thought that dinosaurs could switch from endothermy to ectothermy, cold-blooded and warm-blooded, with size. This would allow dinosaurs to require less food and nutrients to survive when they were larger in size. Oceanic life in the Triassic Ocean. Following the end Permian extinction, oceanic life was very limited. The Triassic period was an important time in history. It was mainly recognized for the first time in which dinosaurs walked the earth. However, many other important things happened. Episodes of acidification occurred within the oceans, which directly affected the metazoan reef building, thus having a lack of coral reefs in the early Triassic. Basically, during these extinction events, there's no history, or there's no record in the fossil record of coral reef building at this time. It pretty much goes away. Following the end Permian extinction event, the ancient corals that were popular at the time died out, and what we know now as modern corals survived and flourished, which is the reason why we have the corals that we have today. The oceans in the Triassic era were heavy in acidification close to the equatorial surface. Temperatures would also rise and exceed 40 degrees Celsius. Oceans were also high in anoxia and toxicity. Anoxia is when water has a lack of oxygen, thus this leads to having a greater quantity of oxidation by bacteria than oxygen in the waters. In conclusion, the Triassic period was a turbulent time in the Earth's history. The Triassic period shows us how natural geologic events can greatly influence life on Earth, and the aftermath of these events led to much of the world as we know it today. For more information, visit the National Science Foundation at www.nsf.gov, the Kansas Geological Survey at www.kgs.ku.edu, and the works cited and links included on the page for this video below here.